So the lesson today is about acids and bases. It is what you can see displayed here. And the main content of today will be looking at the various definitions of acids and bases. This is what we are calling the acid-base concepts. Then we look at the acid-base strengths. And lastly, we look at the outer ionization of water and the pH. So having said that, what follows are learning objectives and the outcomes. And therefore, I will skip them to go straight to start with the main content of today. And that is in slide 8, what I have shown there. What you can see here are two bottles. One is written aqueous HCl, and the other one is written aqueous ammonia. Aqueous HCl, this is hydrochloric acid in water. And this is what we call ammonium hydroxide. Aqueous ammonia is ammonium hydroxide. So this is an acid, and this is a base. Now, one example that we can give of an acid-base reaction is when a gaseous hydrogen chloride reacts with aqueous ammonia. Gaseous ammonia. In this reaction, you are going to get some white fumes, and these white fumes are the ammonium chloride, which is given here. Now, the equation for that reaction is what you can see here. So this is the hydrogen chloride gas, and this is a ammonia gas. And when they react together, they give you ammonium chloride. Now, this is an example of an acid-base reaction, but the definition of these two as one of them as an acid and the other one as a base will actually be clarified when you look at the three different concepts of an acid and a base. So let us start with the Arrhenius concept of acids and the bases. When we talk about the Arrhenius concept of acids and bases, we say that an acid is a substance which, when it dissolved in water, will produce hydronium ion. Hydronium ion is this kind of an ion here. Actually, what you have here is what we call an acid in water. This is an acid in water, and we can present it this way. Let me look for my pen. Just a moment, I look for my pen. We still have students joining, that's why I'm still admitting them. So here, you have a proton, and you know proton is what we refer to as a free acid. When you add water here, what you get is the hydronium ion, the H3O plus. This is a acid in water. So when we talk about the Arrhenius acid, this is a substance which, when dissolved in water, is going to increase the concentration of the hydronium ion, or that particular substance is going to produce some hydrogen ions. On the other hand, when we talk about Arrhenius base, these are substances which, when dissolved in water, will increase the concentration of the hydroxide ion, the OH here. So that is how we look at the concept of acid and base with regards to the Arrhenius concept. Now we go on. Now, this definition, you find that it is limited because when we talk about it producing hydronium ion, and hydroxyl ion, it means that the substances that are taking part in the reaction must be aqueous. And therefore, the first reaction that we looked at, if I may take you back to this reaction here, then here we will not talk about an acid-base reaction with regards to Arrhenius concept, because we do not have increase in the hydroxyl ion. We don't also have increase in the hydronium ion. So with that, then this one is not covered. So that's why we are saying that the Arrhenius concept is limited, because it considered acid-base reactions only in aqueous solutions and limits bases to compounds that contain the hydroxide ion. So we look at another one, which is the Bronsted-Lowry theory of acids and bases. And this is defined here. When we talk about the Bronsted-Lowry concept of acids and bases, we say that an acid-base reaction is considered a proton transfer reaction, so that one species releases the proton, another species accepts the proton. For example, if you look at what is happening here, we do have, let me select a pen, just again. If you look at what we have here, this is the hydronium ion. The hydronium ion is, we said, is water and an acid. And what is happening here is, now this acid is being lost and transferred to ammonia. So that is what is happening here. So you can see there's a transfer of a proton from the acid here all the way to the base, so that we get water, because after the hydronium ion loses its hydrogen ion or the proton, it forms water. And when this ammonia gains an extra proton, it forms the ammonium ion. So this is an example of an acid-base reaction with regards to the Bronsted-Lowry theory of acids and bases. You can also see here it being explained further. And we can see that this hydronium ion here has donated a proton to the ammonia. Now, the donation of a proton to ammonia is actually a complete transfer of a proton from the acid to the base. And therefore, we can say that the acid is the species that donates the proton in a proton transfer reaction. We can also say that it is a proton donor. On the other hand, when we talk about a Bronsted-Lowry base, it is a proton acceptor. It is the species that accepts a proton in a proton transfer reaction. And this is happening here, where you have it moving from ammonia, accepting a proton to give you the ammonium ion, while the acid here is moving from hydronium ion here to water. Now, the substances in the acid-base reaction that differ by the gain or loss of a proton are what we call the conjugate acid-base pair. Here we talk about a conjugate acid and we talk about a conjugate base, which I'm going to define and give examples. And we can say that the acid is called the conjugate acid, while the base is called the conjugate base. So you can see in the same reaction that we considered here, that you have this hydronium ion is an acid, and once it accepts once it gives out a proton, once it loses a proton, it forms water. So this water is what we are calling a conjugate base. So this base here, which is ammonia, is accepting a proton, and in the process, it is forming ammonium ion. So this ammonium ion is the conjugate acid. So if we were to give formal definitions of what a conjugate base and a conjugate acid is, we would say a conjugate base is a substance formed when an acid loses a hydrogen ion. And we call it a base because it can gain the hydrogen ion and form the acid. Like you can see here, this is what is being formed. This is a conjugate base that has been formed after an acid has lost a hydrogen ion. And we are calling it a base because, you know, it can lose. It can lose or it can regain that particular proton and form the acid. On the other hand, a conjugate acid is the substance formed when a base gains a hydrogen ion. And why do we call it a conjugate acid? This is because it can lose the hydrogen ion and form the base again. And this statement here, so sometimes we may be asked to distinguish between a conjugate base and a conjugate acid. This is the right distinction of the two. So when a base and an acid differ by one proton, one is said to be a conjugate of the other. And I'm giving examples here. For example, when you look at hydrochloric acid. So when hydrochloric acid loses a proton, a chloride ion is formed. So this chloride ion is what we call the conjugate base because it is formed after an acid has lost a proton. Number two, when hydroxyl ion gains a proton, it forms water, meaning that this water is what we call the conjugate acid. Because if it loses that particular proton, then it is going to form the base. So when hydrogen carbonate gains a proton, it forms this weak carbonic acid. If you look at this compound and this compound here, they only differ by one proton. So this carbonic acid is what we are calling the conjugate acid. And if this hydrogen carbonate ion loses a proton, it is going to form a carbonate ion. And this carbonate ion becomes a conjugate base. Other examples of these distinctions are given here. Look, what is the conjugate acid of water? And what is the conjugate base of water? You know, for you to get the conjugate acid of water, this is actually formed when the water has gained a proton, and therefore it is the hydronium ion here. For the conjugate base, this is when water has lost a proton, and therefore you are talking about the hydroxyl ion. Are you following, students?
Yes.
I hope I'm not too fast.
No.
In the event that I'm fast, please let me know so that I can go slowly. Other examples. In the following equations, label each species as an acid or a base, then show the conjugate acid-base pairs. Now, this is a hydrogen carbonate ion. This is a hydrofluoric acid. And this is a weak carbonic acid. And this is a fluoride ion. This is a a hydrogen carbonate. This is hydroxyl ion. And this is a carbonate ion, and this is water. So the question is, which of these is an acid and which of these is the base? So look at what is happening here. In the transition from the carbonic acid, hydrogen carbonate here, to carbonic acid, what has happened? You can see there is acceptance of a proton. So that substance which accepts a proton, what is it? Is it a base or an acid? Now,
A base.
it is a base, very good. If you look at hydrofluoric acid, I'm actually calling it hydrofluoric acid, and you can see it's already an acid. So this is a base, this is an acid, okay?
Yes.
This is an acid, this is a base, and you can look at the conjugate acid-base pairs. The conjugate acid-base pairs are those that differ by one proton. Therefore, in A, you have hydrogen carbonate and the carbonic acid. These are conjugate acid-base pairs. Now, this hydrofluoric acid and the fluoride ion also differ by one proton. Actually, that is explained in the slide that follows. So you can see we are saying that this hydrogen carbonate is a base, and this hydrofluoric acid is an acid. This weak carbonic acid is an acid, and this fluoride ion is a base. And we are saying that this carbonic acid, hydrogen carbonate, and this carbonic acid are actually conjugate acid-base pairs in the sense that they differ by one proton. That's why we are saying that the carbonic acid and hydrogen carbonate are the conjugate acid pairs, and also the hydrofluoric acid and the fluorine are conjugate acid-base pairs. The same thing applies to this. If you look at what is happening here, this is an acid, and this is a base. You know, the definition of a compound as an acid as a base, actually, as we are going to see when we are looking at amphoteric and amphiprotic, will depend on what the other reactant is or what the media for the reaction is. So like you can see, this hydrogen carbonate here is a base. The same hydrogen carbonate here is an acid. I will define, I will clarify why it is behaving like that. So you'll realize that this is a base. Here it becomes a base, the water becomes an acid. And therefore, when you look at the hydrogen carbonate and the carbonate ion, these differ by one proton, and therefore they are conjugate acid-base pairs. Similarly, this hydroxyl ion and the water differ by one proton, and they are also conjugate acid-base pairs. So let me revisit this hydrogen carbonate here acting as a base, and hydrogen carbonate here acting as an acid. So we say that a species that can either act as an acid and as a base, depending on the other reactant, are called amphoteric species. And I am going to introduce another terminology here called amphiprotic. And I want to distinguish between the two. When we talk about amphiprotic actually refers to the ability to donate or accept electrons. But amphoteric refers to the ability to act as an acid or a base. Now, the question therefore is amphiprotic and amphoteric the same? The answer is no, they are not the same. Actually, we can say all amphiprotic substances are amphoteric, but not all amphoteric substances are amphiprotic. And let me give an example. You have something called aluminum oxide. there is a aluminium oxide. This is an oxide which we know from chemistry can act as a base and as an acid. Now the question is it amphoteric or is it ambiprotic? Now, in the behavior of acid and base for this aluminium oxide, there is no transfer of protons from one species to another. And therefore, this compound is amphoteric and not ambiprotic. Remember, I said an ambiprotic refers to the ability to donate or accept protons. Therefore, we can say that all ambiprotic substances are amphoteric, but not all amphoteric substances are ambiprotic. And for example, we are saying that some oxides are amphoteric, but they are not ambiprotic because they cannot release or accept protons. And I've given an example of aluminium oxide. This aluminium oxide does not have any protons that it can exchange with any other species. Now, so we are saying that this hydrogen carbonate was a base in the first reaction. So if you look at what we have here, it is a base and it is an acid in the second example. But its behavior of acid and a base actually is involving the transfer of protons from one species to another. In this particular case, it is transferring, no, it is accepting a proton from hydrofluoric acid. In this particular case, it is transferring a proton to hydroxyl ion. So this one is actually an ambiprotic species. Okay? It is ambiprotic species because its acid-base character involves the transfer of protons from one species to another. Now we go to.
Excuse me, please.
Yes.
I didn't understand the difference between the two.
You didn't understand the difference between the
Difference
two?
Between amphoteric and ambiprotic.
Very good. Now, amphoteric is a broad terminology that defines a species that can act as an acid or a base depending on the other reactant or depending on the media. Now, ambiprotic is specific in the sense that in its behavior of an acid and a base, there is proton transfer and a proton acceptance. And I gave an example of aluminium oxide. We know from chemistry that this compound here can act as a base and as an acid. If you look at the compound here, it doesn't have any protons that it can transfer to another species. Therefore, this is acting as a base. It is also acting as an acid, but it does not involve the transfer of electrons from one species to another. So that species is amphoteric, but it is not ambiprotic. Now, if you look at the hydrogen carbonate, if you look at this, we have seen in one example, let me quote this example. You can see here, this hydrogen carbonate here is behaving as a base because it is going to accept a proton from hydrofluoric acid. So it is a proton acceptor here. In part B, it is an acid because it is a proton donor. So this property of the hydrogen carbonate to behave as an acid and a base via the donation or acceptance of protons is what qualifies it to be ambiprotic. And that is why I'm saying that this one is amphoteric and amphiphotic. Amphiphotic. While this one is only amphoteric. And not amphiphotic. Is it clear now? The student who had asked the question. Students, are you hearing me?
Yes.
Yes, we can hear you.
Can hear you.
So is it clear to the student who had asked?
Maybe she's not. doing-
Okay, when she comes up, she can revisit the question. I will be able to explain further. But that's why we are saying that a species can be amphoteric, but not amphiphotic. So we go to the other concept of acids and bases. This is what we call the Lewis concept of acids and bases. And we say a Lewis acid is a species that can form covalent bond by accepting an electron pair from another species. While a Lewis base is a species that can form a covalent bond by donating an electron pair to another species. So here we are defining an acid and a base as a proton donor, an electron donor and an electron acceptor. And an example is illustrated here. So here you have boron trifluoride. In our one of our previous lectures, we gave this boron as one of the species central atoms that is deficient in terms of the number of electrons that it requires. We explained that it is going to be surrounded by 6 instead of 8. But look at what is happening here. This boron trifluoride here, you react it with the ammonia. Remember, ammonia has a lone pair of electrons, and this boron here is electron deficient. Therefore, what is going to happen here is this, that there is going to be donation of a pair of electrons from the ammonia. When you talk about ammonia, the actual species that is giving out the electrons is the nitrogen, and that is going to be donated for sharing with the boron, and this is what we get. So this is an example of a Lewis acid and a Lewis base. So you can see this is accepting an electron pair, while the Lewis base is donating an electron pair. Another example that we can give is the reaction between the silver ions and ammonia. This is actually what we call coordination chemistry. So when you look at what is happening here, you have ammonia here coordinating to two, silver coordinating to two ammonium ions. And therefore, remember, this silver here has already lost an electron. Therefore, you can see the silver forms ion, or the silver ion forms a complex with two ammonia molecules. And you can see here there is a donation of a pair of electrons from the nitrogen. This is the lone pair of electrons from nitrogen all the way to the silver. And therefore, the silver ion here becomes an electron pair acceptor, while the ammonia here becomes the electron pair donor. Therefore, the electron pair donor here is a base, and the electron pair acceptor here is an acid. Now, how do we tell the relative strengths of acids and the bases? Somebody want to know?
Question.
Yes,
Can you go back to the previous slide?
this slide here.
Yeah.
Yes.
The way this silver reacted with ammonia,
Mhm.
can you show, like, we had two ammonia, and you know how the formation of this complex, can you remind us how, like, you form the complex, you react? you make a
That-
reaction to get the
Now,
product.
this is not actually formation of an ionic compound. This is formation of a complex compound by coordination. All right. So the lone pair of electrons are going to be coordinated to the silver. It is not a complete transfer of electrons the way we have the formation of ionic compounds. This is coordination chemistry or the formation of complexes.
Yeah, but we have two ammonia.
Yes,
I mean, like this silver needs only one ammonia.
yes.
So, and we have two molecules of ammonia.
It doesn't need one ammonia. Okay. This is a case. This is a case whereby look at it in terms of having the central atom either excess electrons or lower electrons coordinated to it. So it is not a matter of satisfying the octet rule.
Okay.
Yes. So the relative strength of acids and bases, we say that if an acid is stronger, then its conjugate base is going to be weak, and vice versa. And we can have a chart here. This is hypochlorous acid, and this is a chlorate ion. So one is an acid, the other one is a base. So you can see this is a strong acid. The base is going to be a very weak. So there is inverse proportion of these two. And let me give examples here. Formic acid is what we call methanoic acid. It is stronger than acetic acid. Acetic acid is what we call ethanoic acid. Now, if I write this, H C O H, that is what we call the methanoic acid, and it is going to give us, when it ionizes, it is going to give us HCOO plus an hydrogen ion. And then when we have the ethanoic acid, we have CH3COH. And when it ionizes, it gives us CH3COO plus a hydrogen ion. Now, we are saying that this methanoic acid here, let me do away with this. We are saying that, I want to pick a pen. We are saying that this methanoic acid here is stronger than the ethanoic acid. Now, there are ions that this one here is supposed to be weaker than this one here. That's what we are saying. That's why we are saying that because the methanoic acid is stronger than the acetic acid, I really don't like calling them formic acid. I'd rather call them methanoic acid and ethanoic acid. So the ethanoid ion, which is the conjugate base of the acid, will be weak. So if this is strong, this one, let me do away with the drawings. Okay? So if this is strong, then this one will be weak. If this is weak, then this one will be strong. And that is what is explained in this statement here. Another example that we can give, look at this. For the following reaction, decide which. Now, this one is coming earlier because here we judge which side a reaction is likely to move depending on the strength of the base or the acid. And the general statement, which will come also later, is that the preferred direction of reaction is the one that produces the weak substances, the weak acid and the weak base. So we are saying this, that while comparing the relative strength of the two acids, that is hydrogen cyanide and the hydrogen sulfate, it is going to be noticed that this cyanide here is weak. And when we compare the sulfate and the cyanide ion, you also realize that the sulfate is weaker. Therefore, you would expect the reaction to move in this direction. And why is it moving in this direction? It's because this opposite direction here is the one that produces a weak acid and a weaker base. This side contains the strong species. This side contains the weaker species. So the direction is going to be favored that which produces the weaker species. Let me talk about molecular structure and the strength of an acid or a base. Now, when we talk about how strong an acid is or how weak an acid is, this depends on how easy it is for us to lose that particular proton. How easy it is for the proton to be transferred from the acid to the base. That's why we are saying that the strength of an acid depends on how easily the proton is lost or removed from the bond in the acid species. The more polarized the bond between hydrogen and the atom to which it is bonded, the more easily is the hydrogen ion lost. When we talk about more polarized, is when these two species have significantly high difference in electronegativities, so that this hydrogen is almost losing the electron, while the other species is almost getting the electron, meaning that it is almost becoming a free hydrogen ion. And if it is almost becoming a free hydrogen ion, then it is so easy for us to lose it. And if it is easy for us to lose it, then that particular acid is a strong acid. We also look at factors that affect how easy it is for us to lose this particular hydrogen ion, and therefore we judge the strength of that particular acid or its weakness. And I'm going to start by this. When we talk about a binary acid, a binary acid is that which is composed of atoms of two elements only. For example, hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. So when we talk about a binary acid, the size of the bond increases along the group in the periodic table, and therefore the acid strength increases. Let me illustrate that. Let me pick this. The moment it has not been picked. Now, you have fluoride. A fluoride looks like this. It's a small one. Then you have a chlorine. A chlorine is bigger. Then you have bromine. A bromine there is much bigger. Then iodine. Iodine is the biggest. Now, remember, each of these has a hydrogen, 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 and hydrogen. Now, the question we are supposed to ask ourselves is, in which of these four cases is the hydrogen held strongest to the halogen? Can I hear from you?
The first one.
Yes.
The first one is very strongest held, isn't it? And
Yeah.
the last one is weakly held, because you can see the increase in the atomic, in the ionic radius of the species that we are talking about, isn't it? Therefore, in terms of the ease with which it can be lost, this one is weakly held, and therefore it is going to be lost easier, isn't it? And therefore it means this is going to be the strongest acid, and this is going to be the weakest acid. This one does not want to lose the proton. This one easily wants to lose the proton. Because of that, we have actually put the strength of the acids in the order that you can see here. Now, if you look at this also, for binary acid going across a row of elements of the periodic table, as electronegativity increases, the bond polarity increases. Now, we are actually looking at, let me pick the pen again. The one, just a moment. So we are looking at oxygen and the fluorine. How do we compare this in the periodic table? Yes?
In terms of what?
Now, how can we compare the electronegativities in the periodic table?
Across the period, the oxygen is more electronegative than the fluorine.
Pardon?
No,
fluoride
across
is
the is more electronegative than the oxygen.
We would expect the electronegative to increase in that direction, isn't it?
Yes.
Yes.
So this is more electronegative. Therefore, if you have oxygen, hydrogen, and hydrogen, then you have hydrogen and fluoride. Now, if we look at the relative sharing of these bonds, now for hydrogen, you may actually say it is here. It is here. Closer to the oxygen, but in this one, it is even more closer to the fluoride, isn't it? Because it is more electronegative. So you would expect it to be even more closer here, meaning that this one is almost losing hope. When it is almost losing hope, it means that it is almost forming free hydrogen ion, and that makes this one an easier compound to lose the proton, and that is why it is a stronger acid than the water.
Sir,
Yes,
can you please just go back before whatever you raised?
which
I
one?
just want to ask a question. You raised the thing you were explaining. Can you just go
Yes,
back?
it is
Yeah.
there.
How is hydrogen closer to fluorine than it is the hydrogen that is closer to oxygen? And how is that one more loose then?
Pardon?
Because if it's closer, you said the hydrogen that's the closest to the fluorine is one that has a risk of getting like lost easily. How is that possible? If it's closer to the fluorine, isn't the attraction stronger?
I'm saying this, listen, I'm talking about the sharing of the bonds. Okay? This fluorine here is more electronegative. Electronegative, you know, it's the tendency
Yes.
of a species to attract electrons to itself in a bond, isn't it?
Yeah.
The sharing, we are comparing the sharing of electrons here and the sharing of electrons here. Okay? We know that the electrons are going to be closer to the more electronegative atom. So in water is less electronegative than the fluorine. Therefore, the sharing of these electrons here is going to be closer to the oxygen in this particular case. But in fluorine, it is going to be even more closer to the fluorine here. The question therefore is, if we judge the tendency of this hydrogen forming a hydrogen ion and this one, you'll realize that because the electrons here have been taken very close to the
Oh,
fluorine.
sorry. Yeah, okay. I see what you mean.
Yeah, so you understand?
Yes, thank you.
Okay. There is another question raised by Nicholas. Another
Yes, Prof.
hand.
Please,
Yes,
can you go back to the previous slide?
previous slide. Let me go there.
I'm actually kind of confused. Like,
Yes.
what is the actual trend across the period and down the group? Because here, I think the trend here also is increasing down the group, and the one we just did is also increasing. And my question is, if fluorine is having the highest electronegativity, won't it have the highest, like the strength of the acid, won't it have the highest rather than iodine having the highest?
Now, here we are looking at the size of the atom with respect to how strongly held. Because what we are comparing here, look, what we are comparing here and what we are comparing here are totally different things. Here, we are comparing halogens only. But here, we are comparing oxygen and a halogen. So it is a different trend here. If you look at what we have here, all of them are hydrogen, 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 hydrogen. But here we have fluorine, a chlorine, bromine, and iodine. Okay?
Yes, like my question is, like the bond, let's say in hydrogen fluoride, hydrogen is almost losing the electron, the bonding electron. But in hydrogen iodide, it's kind of like equally shared, even though it's not, but like, I don't know.
Come again.
Okay, I was saying that in hydrogen fluoride, hydrogen is almost losing the electron.
Are you talking about this comparison or this comparison?
No, the first one, the halogen.
The first one, yes.
Yeah. Like the bonding electron is much more closer to fluorine, more than the rest.
You know, you look at it in terms of, actually, look at it in terms of the effective nuclear charge. Right?
Yes, yes.
You
I
look at it in
understand,
terms of, because these are halogens, and the effective nuclear charge in halogens actually is going to decrease as you go down a group.
I get it, Prof. Thank you.
So the question would be, which of these one would be held strongest? Which of these would be held strongest? Here we are looking at it in terms of bond polarity, if I may say so. Can I continue?
Yes, Prof.
Okay. So the other examples are here. These ones, again, you can look at which of the two is strong, which one is not strong. So you can see for hydrogen fluoride and hydrogen chloride, these are binary acids from the same group. So you just compare the sizes of fluorine and the chlorine, and we are seeing that the chlorine is larger. And if it is larger, it means that the hydrogen in that particular case is weaker, it's weakly held, meaning that that is a strong acid. So this is just for your exercise to look at how that trend can be explained. Okay, so that is that. Water and sulfide, again, you can look at that. Now, this is another factor that we can look at. Now, for a series of oxo acids differing only in the central atom Y, the acid strength increases with the electronegativity of Y. So what we are looking at here, what we are looking at here is this species here and that species here. Now the question is, between chlorine and bromine, which one is more electronegative? You would expect this chlorine to be more electronegative than bromine, and therefore you can see in effect, this hydrogen here is being pulled effectively towards the chloride, and here it is being pulled effectively towards the bromine. And because both of these species have different tendencies to attract the electrons, the pulling here is stronger than the pulling here. So if the pulling here is stronger, then it is going to leave it with almost a free hydrogen ion, making it a stronger acid. It is easier to lose this hydrogen here than it is to lose this hydrogen here in terms of the relative electronegativities. But when you have, for oxoacids, we also look at several factors. And one of the key things to look at is the number of bonding oxygens, the central element, and the charge of the species. And you can see here, for a series of oxoacids, actually the strength will be increasing as the number of oxygen atoms increase. In this particular case, you know, the number of oxygen atoms here is the one that is the central atom. Here, we do not have an oxygen in the central atom. You know, this is hydroxyl ion, so it is not, we cannot consider the oxygen here as a central atom. So this is N is equal to 0, here N is equal to 1, here N is equal to 2, and here N is equal to 3. So as you increase the number of oxygens, then the strength of that particular acid is going to increase. So for that reason, we can also say that the acid strength of polyprotic acids and its anion decreases with the increasing negative charge. So as you increase the negative charge, then that particular strength is going to increase. For example, if you compare these two, the charge here is 0. And the charge here is -1. And therefore, as you move from 0 to -1, there is a decrease in the strength of that particular acid, meaning that this is stronger, this is weaker, and the trend continues for the others. So can I take attendance as a form of break?
Yeah, sure.
So let me go to the attendance. Okay, let me check. I'm starting with Y. At the moment. So attendance for Y is loading. Okay, we begin. Mustaf Abdinor,
Yes, present.
Alice Alang.
Present.
Okay. Anei. Anei.
Present.
Daniel Bilin.
Present.
Samuel.
Present.
Good. Leju.
Present. Present.
Kempabazi. Lillian.
Present.
Then Lucy Lojore.
Present.
Isaac Makuku.
Present.
Then we have Ivy Moshere.
Present.
Prince Moses.
Present.
Grace Mugambi.
Present.
Angela Murithi.
Present. Present.
Mary Murunga. Mary.
Present.
Michelle Murunga.
Present.
Are you siblings?
No.
Okay. Prudence Ndiritu. Prudence.
Her mic is not working, but she's in class.
Okay, thanks for the information. Charity Juguna.
Present.
Barbara Omenya.
Present.
Yesh Patel.
Present.
Cecilia Selempo.
Present.
Alexa Mhonza.
Present.
Lucy Wainaina.
Present.
Naiguran Weni.
Present.
Thank you. Now we go to the other class. Just a moment, I load it. Anita. Anita.
Present.
Nicholas Ameso.
Present.
Obwage Denver.
Present.
Lydia Edosa.
Present.
Isabella Gardner. Isabella.
Present.
Lillian Gishengo.
Present.
Amin Hassan.
Present.
Asna Hassan.
Present.
Maria Janowala.
Present.
Edin Kisoka.
Present.
Michelle Mogusu. Michelle,
Sir, she's present, but her mic isn't working, but she's just typed in the chat, I'm present.
thank you. Yeah, I can see people are chatting there. Joy Mushemi,
Present.
Anastasia Munjuri,
Present.
Philip Mutinda,
Present.
Alice Odiwar.
Present.
Alice,
Present.
Maria Consolé Patience,
Present, sir.
Kush Rana,
Present.
Sebata,
Present.
Grace Thuku,
Present.
Lorraine Wainaina,
Present.
Njoki Waweru.
Present.
So thank you. So we can continue with our lecture then. So here you can compare the strengths of the acids depending on the charge that we have, and I have explained that when sorry, when the negative charge increases, that particular acid decreases in strength. Now, this example you can see here is something we have talked about in the past. It comes from this statement: a reaction will always go in the direction from stronger to weaker acid and from stronger base to weaker base. That's why I said that this equation here, we saw it in our previous, some of our previous slides. And I explained that it is going to be favored in the direction that produces the weaker acid, or the weaker species, that is the weaker acid and the weaker base. Now, after that, we go to the self-ionization of water. I would not wish to discuss this one today because we still have another lesson on Wednesday. In fact, I intend to finish this part on Wednesday. Therefore, I would wish to stop here for today so that when we meet on Wednesday in the morning session, we start with the self-ionization of water. We look at how you can calculate the pH of an acid and a base and such kind of things. Is it okay, students?
Yes, sir.
Yes.
Okay, let me also say this. I understand this afternoon you will be doing your quiz too. That quiz, we already loaded it. So it's going to be available, and we have made enough announcements for you to be aware on the platform that the quiz is already there. Important is that the content that I have taught today is not tested in that quiz. Okay?
Thank you.
Okay.
So, sir, it's only from week 8, if I'm not wrong, like after mid.
What that it covers what we learned after your mid semester exams
Okay.
up to the previous week. You
So until
understand?
molecular geometry.
Yes, until molecular geometry.
Okay.
So the content for today is not covered. It is going to be there, I mean, in the final examination. Lillian, you have raised your hand.
Yeah, I was asking for your recordings. I've never received any.
They are there. The recordings are there. I loaded them last week. Were you able to see them?
No, I haven't.
Yes, some of us have seen.
Why have others not seen?
Maybe she has not checked.
Yes, they are there. Please check. The recordings are there.
Or
Okay,
maybe because she's in a different group, so there's Y and Z if I'm not wrong.
I put in both.
Okay, then I don't.
I put in both. I think the one that may not be there is the molecular geometry. That one was taught by my colleague.
Yeah.
But for all the others that I taught, the recordings are there. Even the recording for today is going to be uploaded after the Zoom makes it available.
Okay, thank you.
Any other question?
What time are we doing the quiz?
It is supposed to start at 3:30 today. Please check the announcements. We are also going to announce it on the WhatsApp forum for you to be aware. Is that okay?
Okay.
So thank you very much. I wish you well in the quiz. Let us meet on Wednesday in the morning so that we can finish the remaining bits of our content.
Right.
Thank you, sir.
Okay.
Bye.
Bye-bye.
Bye-bye.
Thank you.
Bye.
Wow.